Hi boys and girls, this video comprises the lecture for section 10.4 on page 729, and the section is entitled Polar Coordinates and Polar Graphs, and I think this is a really fun section. And what we're about to discover is that the ways that we have been graphing up until now are going to change in new and exciting ways. Now, I say that fully aware that you may have seen this already in pre-calculus, and if so, that's great. But we're going to go through it again and make sure that we understand the basics of polar coordinates and polar graphs. Starting with polar coordinates. Today, we are now, that means before this lesson, able to represent graphs as a collection of points, x comma y, on a rectangular coordinate system, using equations that are either in rectangular or parametric form, since we've discussed that. In this section, we are introduced to the polar coordinate system, something a little different. To form the polar coordinate system in the plane, we fix a point O, called the pole or the origin, and we construct from O an initial ray called the polar axis. Notice here's the polar axis, kind of looks like the x-axis. Then each point P in the plane can be assigned polar coordinates r, comma, theta, where r is the directed distance from O to P, and theta is a directed angle counterclockwise from the polar axis to the segment OP. Here's what that means. We have been used to assigning rectangular coordinates to the point P, a horizontal distance and a vertical distance, resulting in some sort of xy that would represent its location in the coordinate plane. Now we're going to do it a little bit differently. We're going to use the angle that is formed from the polar axis, sort of the starting place, to the ray that is formed by connecting the origin and the point. That angle, theta, will be the second coordinate of our ordered pair, and then the first coordinate will be the actual distance from O, the pole, to the point. So think about it this way. You can kind of see that a right triangle is formed. We have been using x and y, the lengths of the two sides, to represent the position of this point. But now we're going to use the length of the hypotenuse instead, and that is what r is. It stands for a radial distance from the O, from the origin or the pole, to the point. Okay, so let's look at a couple of graphs. The diagram below shows 3 points on the polar coordinate system. I'm sorry, boys and girls, that's my fax machine, just ignore it. Notice that in this system, it is convenient to locate points with respect to a grid of concentric circles intersected by radial lines. So obviously this small circle right here represents any point from the origin that is a distance of 1 from the origin. Any place that you draw from the origin to that circle is a distance of 1. The r would be 1 there. So it's kind of convenient to use this circle to represent the distance of 1 from the origin. Similarly, it makes sense to use a circle of radius 2 to represent the distance of 2 from the origin. The radial lines, of course, are the lines that you draw from the origin to any point in the plane. So notice in this case, we're talking about this point. It is on the circle of radius 2, so the radial distance from O to the point is 2. And then pi over 3 is representing the angle that is formed with the polar axis and the ray that we formed by connecting the origin to the point. So the polar coordinates are 2, comma, pi over 3. Now let's look at this diagram. Here's the point that we're discussing. The radial distance from the origin is 3. As you can see, it lies on that circle of radius 3. And then if we're measuring from the polar axis to the ray that is formed by connecting the origin to the point, it's negative pi over 6, negative 30 degrees. And so the polar coordinates for this point, 3, comma, negative pi over 6. Look over here, boys and girls. Looks like the same point. It is the same point. It does have the radial distance of 3, but now instead of going from the polar axis in a clockwise direction, we're going to go counterclockwise to measure that angle. And of course we can do that. So instead of it being a 30 degrees or a negative 30 degrees from the polar axis to the point, Instead, we're going 330 degrees in the positive direction, in the counterclockwise direction to get there. The idea being that each point on the polar coordinate system may have more than one set of polar coordinates that correspond to it. In fact, there are really infinitely more, because you can probably see, well, what if I go around another 2 pi? Isn't that the same point? And maybe another 2 pi. So this angle can keep changing as you keep rotating around the circle, and yet it is resulting in the same point in the coordinate, in the polar coordinate plane. With rectangular coordinates, each point xy has a unique representation. This is not true with polar coordinates. For instance, the coordinates r, theta and r, 2 pi plus theta represent the same point. Just like we said, any point that you choose, if you rotate around another 2 pi, you end up at the same point. Also, because r is a directed distance, the coordinates r, theta and negative r, theta plus pi, represent the same point. So to generalize this, the point r, theta, our basic set of coordinates for any point in the polar coordinate plane, can be written this way: r theta plus 2n pi. 2n is a way that we represent an even number. So they're saying your angle plus any even number of pi rotations will take you back to the same point. And here we could have negative r, theta plus 2n plus 1 pi, and that would also result in the same point as r, theta. 2n plus 1 is the way that we represent an odd integer. So they're saying negative r and theta plus any odd multiple of pi will take you to the same point as r theta. So just keep that in mind as you sort of investigate the number of ways a point can be represented in the polar coordinate plane. The pole is represented by 0, theta, where 0 can be any, where theta can be any angle. And that kind of makes sense. If the first coordinate r represents the distance from the origin to the point, well, if you're at the origin, the fact that you have gone 0 distance means you're at the origin. It doesn't really matter what the angle is. If r is 0, then you're talking about the origin. Now that we have just fallen in love with these new polar coordinates, let's practice converting from polar coordinates to rectangular and back again if we'd like. To establish the relationship between polar and rectangular coordinates, let the polar axis coincide with the positive x-axis. So our polar axis, we're going to call that the x-axis. And of course, let the pole be on the origin, as shown in this figure. Because xy lies on a circle of radius r, it follows that r squared equals x squared plus y squared, right? Because think about it. Remember, as I said before, you've got this ray, which is this distance r is the hypotenuse of a right triangle that is formed by the x distance, the y distance, and the hypotenuse. It makes sense that this distance, r squared, would equal x squared plus y squared because of the Pythagorean theorem. So that's a relationship that's going to help us convert from polar to coordinate to rectangular and back again. Also, when r is greater than 0, the definite of the trigonometric functions implies that, I am not sure what that sentence is supposed to say, but we'll say this. Notice that as you're looking at this triangle and theta, you can see that these relationships apply. Isn't it true that the tangent of theta is y over x? Isn't it true that the cosine of theta would be x over r? Isn't it true that the sine of theta would be y over r? So these three relationships will help us also to convert between rectangular and polar coordinates. Now, let's take sine of theta equals y over r and solve for y. Isn't it true that you could multiply both sides by r and get y equals r sine theta? Similarly, let's solve cosine theta equals x over r for x, and just multiplying both sides by r would give you that x equals r cosine theta. Using these two relationships, if you have something that is in polar coordinates, if you have r and theta, you convert can convert to an x and a y value. Now let's look at these two relationships. Tan theta, as we said before, is y over x. We also have that r squared equals x squared plus y squared. So that means if you're given xy coordinates, you could use this relationship to find theta, you could use this relationship to find r. So this little section is converting rectangular to polar, and these two relationships will be converting polar to rectangular. So chances are the next example is going to ask us to do just that. If you're following along in your book, and you should be, we're on page 730, example 1. First of all, we're going to do polar to rectangular conversion. Let's remember those two relationships that are going to be so helpful. We discovered that x is equal to r cosine theta, and y is equal to r sine theta. So let's change colors for dramatic effect. For our particular polar coordinates, that means x is going to be 2 cosine of pi, and y is going to be 2 sine of pi. Well, cosine of pi, as we know, is -1. So this means that our x is going to be 2 times, let's just back up a little bit here and make this more logical, is going to be 2 times -1, which is -2. For our particular y-coordinate, this means that it's going to be 2 times 0, since the sign of pi is 0, which is 0. So the rectangular coordinates that correspond to the polar coordinates 2, pi are -2, 0. Does that make sense? Let's make that a little bit better. -2, 0. That was fun, wasn't it? Let's do it again. Here we have our two relationships, x equals r cosine theta and y equals r sine theta. In this case, r is the square root of 3 and theta is pi over 6. So for our coordinates, x will be equal to the square root of 3 and then cosine of pi over 6. Ooh, that's scary because we don't know what that is. Y is equal to the square root of 3 sine of pi over 6. Double scary, we don't know what that is. Do not reach for your graphing calculator, boys and girls. Let's draw a triangle. Pi over 6, of course, is a 30-degree angle, and I'm going to draw my little representative 30, 60, 90 triangle here. The small angle is 30, the large angle is 60, and as I said in class today, 90 is never the answer. Opposite of the 30-degree angle is 1, the hypotenuse is 2, and then we have square root of 3. Well, pi over 6 is 30 degrees. The cosine is the square root of 3, adjacent over hypotenuse, the square root of 3 over 2. So this is going to be square root of 3 times square root of 3 over 2, and that is 3/2. That's the x-coordinate. Now we need the sine of pi over 6. The sine of pi over 6 is opposite over hypotenuse, and so that's going to be square root of 3 times 1/2, which is the square root of 3 over 2. Therefore, the rectangular coordinates that correspond to the polar coordinates square root of 3 pi over 6 are 3/2 square root of 3 over 2. Okay, now in the next example, we're going to go the opposite way as far as converting is concerned, from rectangular to polar conversion. So let's remember the two little relationships that we need to do that. We need to remember that tan of theta is equal to y over x. Also, we need to remember that r squared is equal to x squared plus y squared. Now let's start with the point -1, 1, which is our rectangular coordinates. It's good for us to know that this is over here in the second quadrant, so that when we find the angle that corresponds to our y over x here, we know which reference angle to use, the one in the first quadrant, second, third, fourth. Since our point is in the second quadrant, we're going to use that reference angle. But first, let's figure out what the angle is. So we're saying tan of theta equals basically 1 over negative 1, which is negative 1. Now, in case you were wondering, boys and girls, that shows up in a 45, 45, 90 degree triangle. These little triangles aren't that great, but this is 45, 45, 1, 1, square root of 2. So I know that the tangent of the 45 degree angle is 1 over 1, or it could be negative 1 over 1 in a different quadrant. So I know that the reference angle is pi over 4. But pi over 4, 45 degrees, is here. And I want the one that's in the second quadrant, which is 3 pi over 4. So for this particular situation, my theta is 3 pi over 4. Now let's figure out what r squared is. This one's a little bit easier because, of course, r squared is going to be negative 1 quantity squared plus 1 quantity squared. That means it's going to be r squared is 2, which means r is the square root of 2. Therefore, the polar coordinates that correspond to these rectangular coordinates are square root of 2, 3 pi over 4. Kind of fun, right? Okay, now these four little relationships, these two and the previous ones that we discussed, you've got to memorize those. So have fun with that. Now let's see how we can graph a polar region, a polar graph. One way to sketch the graph of a polar equation is to convert to rectangular coordinates and then sketch the graph of the rectangular equation. Well, notice here that all we're given is r equals 2. Which means that all we're really going to be graphing is a circle of radius 2. Notice that I've tried to get some polar graph paper here. If this is 5, then 1, 2 means that this circle right here is what we'll end up graphing. But watch what happens when we convert this to polar coordinates. Isn't it true that r squared equals x squared plus y squared? And our r is 2, so 4 equals x squared plus y squared. And of course we recognize this as a circle centered at the origin and with a radius of 2, which is what we would sketch. Now for letter B, what we're going to do is use this relationship instead. Tan of theta is equal to y over x. We're trying to convert these to rectangular coordinates. Well, tangent of pi over 3, once again, that is a 60 degree angle. Pi is 180. 180 divided by 3 is 60. So here comes my little triangle again. 30, 60, oops, 60. And then, of course, it's a 90 degree triangle. I know that the sides are opposite the small side, 1, hypotenuse 2, square root of 3. I'm looking for the tangent of theta, which is opposite over adjacent, and so tangent of 60 degrees is square root of 3 over 1. I should have written this as tan of pi over 3 equals y over x, which gives me now, since tan of pi over 3 is the square root of 3 equals y over x, now let's solve for y. Y equals the square root of 3x, which, by the way, is just a line, right? Where the y-intercept is the origin and the slope is the square root of 3 over 1. Well, that's not necessarily our favorite slope, but remember what this means, this pi, theta equals pi over 3, that essentially we're talking about the 60 degree angle, which would probably be about right here. And basically every point that's on the line connecting with the origin and a 60 degree angle. So that's kind of how you would graph it there. Sorry, it's not looking that great. Now r equals secant theta is not quite as straightforward as the other ones. First of all, what we're going to do is rewrite this as, let's put this as r, wait, change colors, definitely change colors because it's getting a little messy. The color change at least tells you where one set of work ends and one set of work begins. So now we know that secant is 1 over cosine theta, right? If we cross multiply, we get r cosine theta equals 1. Well, do you remember what r cosine theta is? Remember, one of our relationships is x equals r cosine theta. So we're talking about the line x equals 1, a vertical line going through 1. And there you have some graphs. chances are on your homework you're going to be doing a little graphing. Now, let's do a really big graph here. We're not going to convert these to rectangular coordinates. We're going to fill in theta values and r values using our calculator. So what I want to do, even though I wish I could show you, is I'm going to sort of talk you through the process of getting your calculator set up to graph these polar graphs. First of all, you would go to Mode, and notice on the fourth line you've got function, parametric, you've got polar. I'm not sure what the other one is, but make sure it's set on polar. Then when you go to your y equals menu, you'll see that it has r equals. And of course you're going to enter 2 cosine 3 theta, right? And of course when you graph it, you see the beautiful thing that you're about to graph. Isn't that cute? Now, here's also what you need to do. Let's set up our table so that it's going up by increments of pi over 6. So go second window, which takes you to table set. Make sure that it says table start on something like 0. That's just a safe place to start. And then where it says delta table, type in pi over 6. Okay? Now yes, in the table, when you do pi over 6, it's going to be a decimal. So like when you go to your table now, you should see 0, 3, and then 0.5236 comma 0 or whatever. Actually it's 0, 2, my bad. But the point is, boys and girls, that you know that that's pi over 6. The next number will be 2 pi over 6. The next 3 pi over 6. The next 4 pi over 6. So let's set this up. We'll start with 0, and then we're going to have pi over 6, and then 2 pi over 6, which of course is pi over 3, 3 pi over 6, the next number we know because we set it up to be increments of pi over 6 will be pi over 2, and then 4 pi over 6 is going to be 2 pi over 3, just writing these in right now. Then we're going to have 5 pi over 6 will be the next one, which is just 5 pi over 6. I should have just written that in there, no reducing. 6 pi over 6 is pi. Then we're going to have 7 pi over 6. We're going to have 8 pi over 6. Again, I'm just keeping it in pi's of 6, pi over 6's, and then reducing, so you can see that's 4 pi over 3. 9 pi over 6 is 3 pi over 2. 10 pi over 6 is going to be 5 pi over 3. 11 pi over 6 does not reduce. And then 12 pi over 6 is 2 pi. Now, these are all going to look like decimals in your calculator, but you know that each one is a pi over 6 increment. So let's just go ahead and put the r values in. We have here for 0, 2. We have for the first one, oh gosh, I'm having a hard time seeing this, 0, then negative 2, then 0, then 2, then 0. Don't get off track, as she said, as she's getting off track. But then remember, we're at pi now, which we know is 3.14, which is negative 2. And then it becomes negative 6. I think that's 0. Just put 0 for that one. And then the next one is going to be 2, and then 0 again. Those weird things with the e to the negative 13 power. Negative 2. Then keep going. We get another weird 0. And then at 2 pi, we get 2. All right, now watch what happens when we graph this. It's going to be great. We're going to have 0, 2. Now remember, this is the angle 0, the point 2. Back, I realized I made a slight little error because we have to think of these as r comma theta. So 0, 2 is really the point 2, 0. Remember, directed distance r, and then angle measure theta. So it probably would have been better if I'd had the table set up r theta, but that's okay. So let's plot these points. A directed distance of 2 and an angle measure of 0 puts the first point right here. Then we have a directed distance of 0 at a pi over 6 angle. Now pi over 6 is about here. It's about a 30-degree angle. But at that 30-degree angle, we're at 0. So essentially, if we were graphing points in between it would take us around here. Then the next point that we're doing is pi over 3, negative 2. Well, negative 2 is in the opposite direction, but remember, pi over 3 is about a 60-degree angle. So let's imagine this line coming through, and that means that we're going to hit the 2 about right here. Then at pi over 2, we head back to 0, like this. And then at 2 pi over 3, which is over in this direction, we're supposed to hit 2 again over there. And then at 5 pi over 6, we're back at 0 again. And then at pi, we go negative 2. So since pi is over here, but it's a directed distance, the opposite direction takes us back to 2 over here. And there you have it. Now, it's not quite as beautiful as you might see on your calculator. You can see that going through these other points that we have here would simply retrace this shape again. So that's how you sketch a polar graph. Now, I'm going to pause while I get ready for the next slide. Okay, now we're going to discuss slope and tangent lines to some sort of polar curve. As you can see here at some polar coordinates, how would we find the equation of the tangent line? Or furthermore, perhaps even a slope at that point? Well, obviously for this we're going to need the derivative. So we have here the slope of a tangent line to a polar graph. The result in this theorem is going to tell us how to do that. Essentially, notice that you have, if f is a differentiable function of theta, then the slope of the tangent line to the graph of r equals f theta at the point r theta is dy dx, the derivative, dy d theta over dx d theta, which is this series of derivatives of the equations in polar form. But chances are you're going to be using rectangular form anyway. This should look familiar because this is the first derivative of a set of parametric equations, dy d theta, dx d theta. From this theorem, the following observations can be made. Solutions to dy d theta equals 0 yield horizontal tangents. Why? Because this is in the numerator. Sorry, my little tablet's getting all kind of wacko here. This is in the numerator, and when you set the numerator equal to 0, you're going to get the places where you have horizontal tangents. Notice it says that solutions to dx d0 d theta equals 0 yield vertical tangents. That's because dx d theta is in the denominator. Setting that equal to 0 will yield the places where you have undefined slopes, therefore vertical tangents. If dy d theta and dx d theta are simultaneously 0, no conclusion can be drawn about tangent lines. Okay, so in this last example, let's find horizontal and vertical tangents of this particular polar graph. R equals sine theta. And of course they give us a range to look at from 0 to pi. Let's first convert this to a set of parametric equations because remember we have these relationships. Isn't it true that x is equal to r cosine theta? Well, if r is sine theta, then our x is going to be sine theta cosine theta. And then, of course, isn't it true that y is equal to r sine theta? Therefore, since r is sine theta, our y will be sine theta, or sine squared theta. Now, let's take the derivatives of each of these functions. We're going to, first of all, let's take the derivative of the x function dx dt. We're going to have to use the product rule, so it'll be first times derivative of the second, sine theta times negative sine theta, plus the second times the derivative of the first, cosine theta times cosine theta. I have no idea why I did this in such a weird manner, but there you have it. dx dt is equal to negative sine squared theta plus cosine squared theta. All right, let's do dy dt. dy dt is going to be 2 sine theta cosine theta. That one's a little quicker. Now, remember that dy dx is this function over this function when you're talking about parametric equations. But since we're looking for vertical and horizontal tangent lines, what we learned on the previous slide is that you'll get the vertical tangent lines when you set dx d theta equal to 0, because that would be the denominator of dy dx. You will get the horizontal tangent lines when you set dy d theta equal to 0. So let's go straight to that step where we set dx d theta equal to 0 and dy d theta equal to 0. I have t there, but it should be theta. Let's change those. Theta, theta, and theta. Now, I'm guessing, let's use this color. When I set negative sine squared theta plus cosine squared theta equal to 0, I'm going to get these angle measures. At pi over 4 and 3 pi over 4, we're going to have vertical tangents. And notice that's what is shown here. When I set 2 sine theta cosine theta equal to 0, that's occurring at 0 and pi over 2. And notice on our graph at 0 and pi over 2 we have horizontal tangents. So from using these tangents, or these slopes, if you need to write an equation of a tangent line, you could. Now, this is a long video and I'm trying to rush through to get to the end. Notice here that I have pretty graphs. These are some important polar curves that show up. I'm not exactly sure what limacone means, but we have one with an inner loop, a heart shape, which is a cardioid, a dimpled limacone, a convex one, just barely having a little convex region there. We have the rose, which we drew, and with more petals, etc. Circles, we've certainly drawn that before. I like this one because it's the limnoscate, which is like the infinity symbol. You can make it horizontal or askew. And here is another kind of polar graph, boys and girls. Your homework is page 736, 1, 2, 7, 8, 27, 31, 32, 35, 38, 59, 65, 67, 83, 86, 91. That might seem crazy, but it's 15 problems, and so instead of doing like 3 through 45 multiples of 3, I just listed 15 problems, so it's still 15, no more, no less. And that's it, boys and girls.